Today we're going to continue on and we're going to talk about a probability distribution. Right? So for a probability distribution, there are just a couple of definitions. The first is called a random variable. And a random variable is a single number value that's typically represented by X. And it's determined by chance for each outcome of a procedure. So a random variable, even though it says random, it actually has a single numerical value. Those random variables are what are within what's called a probability distribution. And a probability distribution is much like a frequency distribution. And in a frequency distribution, we mainly had counts. For a probability distribution, we have probabilities instead of counts. Now, one thing about probability distribution, that is a description of a probability of each value of a random variable, and is often expressed in the format of a table, okay, which is what we're going to look at, tables. All right, so here are the requirements for a probability distribution. The first requirement says that the summation, so this funny looking E that is sigma or capital sigma, and it's understood to be repeated addition. If you were to add up all of the probabilities, right, so this P of X is probabilities, those probabilities must equal to 1 in order to be a probability distribution. The reason why your probabilities must sum up to be 1 is because 1 as a percentage is 100%. And 100% represents the entire probability. All right, a probability can't exceed 100%. And it can't be less than 0. But in order for a probability distribution to exist, you must simply add up all the probabilities. And if the probabilities equal to 1, then it's a probability distribution. The second requirement is that each probability must be in between 0 and 1. All right. So we kind of talked about that earlier. There is a handout back here. I don't know if I did. Okay. All right, so let's take a look at what I passed out is a Module 2 test review. On that Module 2 test review, we're going to take a look at problem number 20 first. It's the very last problem on the test review. Okay, and what we're seeing is a probability distribution. All right, so let me just explain the probability distribution first. So in this probability distribution, notice that it's listed out in a table format. For this first column, we have our random variable X. For the second column, we have our probability. So that P of X is probability. So this says for families with 5 children, let X be the number of children with genetic condition B. All right. So if I look at this table, the very first row says that one child in the family has a 31.21% chance of the genetic condition B. The second row says 2 children in a family have 11.16% of this genetic condition B. The next row says 3 people have an 18% chance, 4 people have like a 19% chance, 5 people have like an 18.99% chance, all right, of this genetic condition B. It says, can the following table be a probability distribution for the random variable x? In order to determine if this is a valid probability, okay, I'm going to bring up my calculator. And as we see from or saw from the notes, I'm going to just go back for a second. This first condition says that all of your probabilities must add up to give you a 1. So in order to answer problem number 20, I'm going to simply take all of these probabilities, I'm going to add them up, and I'm going to see if they sum to 1. Right? So I'm going to take all of my probabilities, 0.3121. And I want to add these up, 0.3121 plus. And if you add all the probabilities up, we see that they in fact sum to the number 1. So this is a valid probability. Come on, let's start this again. All right, so this should be a okay, I'm going to get it right. So later this should be A. All right. I just added up all of the probabilities. On this same sheet, I want to look at problem number 16. All of these things have something to do with probability distributions. 16. Here is problem number 16. So problem number 16 says find the mean and the standard deviation of a probability distribution. They give us our column for random variable, our random variables. They give us a column for our probabilities. Okay, now since this is telling us that this is a probability distribution, we don't have to verify that these things add up to 1. Okay, but they should if you wanted to check. All right. In order to find the mean and the standard deviation, we're going to find it in much the same way as we found the mean and standard deviation for a frequency distribution. We're simply going to put in the random variable as L1. We're going to put in a probability distribution as L2. We're going to use that one variable statistic. And then we're going to pull out the mean and the standard deviation. So the first thing we're going to do is put the probability distribution in the calculator. So I'm going to hit Stat. I want to edit my list. I'm going to choose that first option. I'm going to put my random variables in L1. So that's 2, 5, 7, 10. I'm going to put the probabilities in the list 2. 0.25, 0.05, 0.15, and 0.55. I'm going to return to the home screen. So that's second in mode. Okay, let me just put some steps. Put the data into the calculator. Return to home screen. Use the one variable statistics. So I'm going to go back into Stat. I'm going to scroll over to Calculate. I want to use one variable statistics. Now for my 83, I'm going to simply put in L1, L2. But if you have a TI-84, I believe it is X list should be L1, and then frequency list is L2, and then I think you should, it's like a calculate at the bottom. Right? But on mine, I have to put in L1, L2. I'm going to hit enter. Okay. So what is our mean? Well, remember the mathematical symbol for the mean, right? Whether we're talking about a sample mean or a population mean, that is X bar. What's the standard deviation? 3.36. Now remember we talked about this S, X, and sigma of X. This S sub X is a sample standard distribution. The reason why you don't see anything is because the calculator understands that this is a probability distribution. And for a probability distribution, since it's 100% of the population, you're going to use this sigma sub X. Does that make any sense? Because if you know the population, which is usually impossible because it's impossible to solicit information from everybody in the population. But on this construct, notice that all our probabilities total to a 100%, which means that that's the 100% population. So for this question, we're going to use that sigma sub X. But notice it only gives you one output. So we're going to use 3.36. All right. Any questions about 16? Put it in your list. Use a one variable statistic. All right, and you can pull out the mean and that standard deviation. Okay. Now on the test, there's going to be one more problem, or excuse me, two more problems that deal with probability distributions. So number 20 was one, 16 is one, number 17 and number 18 all deal with probability distributions. So here is problem number 17, and it kind of bleeds over into the next page on your handout. But it says select the correct histogram for the probability distribution. So this is that probability distribution setup. This first column contains our random variable, and they don't really give us any indication on what this probability distribution stands for, right? But we're given 5 random variables, 0 through 4. They give us the probability for each random variable. We have to match it to a graph or a histogram. So for this first random variable 0, it should be at 0.27. So it looks like this first one is at about 0.27. We can throw this one away, right? Because if we look at it for 0, it should be at 0.27, and that's nowhere close. If we look at the next graph, we can throw this one away as well, because for that random variable 0, it has a probability of 0.05, and our probability should be 0.27. And if we look at the last one, it seems like that could be a candidate, right? So I'm kind of narrowing this down to the first one and the last one. The random variable 1 should be at 0.18. So that looks like it could be about 0.18. If I look at my last one, that overshoots 0.18, right? So our frequency distribution should be A. Okay. Right. So not a very complicated problem there, just matching up your probability distribution with a histogram. Now the next problem, number 18, And this is the last problem that deals with probability distribution. So that's like a total of 4. And also on this review, it also puts how much the questions are worth. All right. So here is problem number 18. All right, it says a certain brand of cookies sells many cookies in packs of 5 and has determined a probability distribution for the number of cookies that they sell in a given day. Use the data to answer the following questions. You may round to 2 decimal places. All right, so looking at this probability distribution, for this first row, the random variable is 0, which means that they sell 0 packs of cookies. The probability of them selling no cookies is 20%. The next row says 5, so this alludes to the probability for selling. Now notice these cookies come in packs of 5. So if we sell 5 packs of cookies, the probability is 0.27. Selling 10 5-packs of cookies, the probability is 0.15. If we sell 15 packs of cookies, that probability is unknown. And if we sell 20 packs of cookies, our probability is 14%. The first question says, what is the probability of selling 15 mini cookies in a given day?
Add up the current probabilities
And subtract from 1. So we're going to add up all of our probabilities and subtract from 1. So now this I'm going to write it out in like an algebraic type format. So this is going to equal to 1 minus the sum of these probabilities. So that's 0.2 plus 0.27 plus 0.15 plus 0.14. Right. So what I'm doing is I'm adding up all the probabilities and then we're subtracting from 1. Okay, so I'm going to just put this in the calculator exactly as I see it. So let me clear out my home screen. This is 1 minus, and I put a begin parenthesis, 0.2 plus 0.27 plus 0.15 plus 0.14, and we have 0.24, or it's a 24% probability that they would sell 15 5-packs of cookies. So I just add up all my probabilities, subtract it from 1. Number 2 says find the expected number of mini cookies sold in a day using this discrete probability distribution. Now, this expected number may be a new word. That's just another word for the mean. That's supposed to be X bar. I have no idea why this thing isn't erasing. That's supposed to be X bar. All right, so we're going to find the mean in the same way we found the mean in that previous probability distribution problem. We're going to put in the random variable as list 1. We're going to put in the probability as list 2. And we're going to use the 1 variable statistic. All right, so I'm going to clear out my home screen. I'm going to go into Stat. I'm going to hit Edit. I'm going to clear out these 2 lists by going to the very top of the list. I'm going to hit Clear and Enter. I'm going to put in the random variable. I'm going to put in the probabilities. All right. I'm going to return to my home screen. I'm going to go back in the stat. I'm going to scroll over to one variable statistic. We're going to put in list 1 and list 2. And we're looking for the mean, which is the expected value, which is 9.25. Okay, so the expected value is just another term for the word mean. All right, any questions about that one? All right, now the last one says find the variance. So if you remember, using that one variable statistic, it does not give you the variance, but the variance.
Is that XY formula?
Well, that's equal to the standard deviation squared. And they do give us the standard deviation, right? So I'm simply going to take this standard deviation, which is 6.7961, and we're going to square it. Now, there is the answer key that's on the back of this. Okay, it doesn't really go through how to solve them. All right, but the answer key is attached. All right, so if we were to square the standard deviation, 6.7961 squared, rounded to 2 decimal places, 46.19. And that is the variance. So be careful on this particular problem. All right, because in the printout, they give you the standard deviation only. You have to square that standard deviation in order to get the variance. Okay. All right, so any questions about the probability distribution type questions?
Just so we don't get an error in rounding, can you remind us how we pull up
Right.
the standard deviation from the calculator so that we can hit the square button? They went over it in one of the videos, and I don't remember how to do it, but that was to avoid rounding error.
He has a silver.
I don't think that functionality
That's a TI
84 deal. Because once I hit the one variable statistics, all of those stats are like locked inside of that output.
So if we go out 4 to the 4th place for anything, we should be okay for rounding error.
So that's what I did.
Okay.
They wanted to round to 2 decimal places. So notice I did not use a rounded number. I just took a couple more digits after that place in which I intend to round, and that should let you bypass that rounding error. Okay.
He has a $300 version of the calculator. We don't.
Oh, okay. He's using a different calculator.
I was able to get it up on my T83.
Okay.
I was able to do it, but I had to.
Yeah, on these calculators, it's like as the higher the number gets, the better the programming is. So since I had an 83, they have more functionality like in the 84. So okay. All right, so that is a probability distribution. All right, that was the last concept in Module 2. So now we're going to go back to the very first problem. Okay, and just kind of work them from this point. All right, and as you're going to see, a lot of these things are pretty much the exact same problems that we've been doing through the lecture. All right, so looking at this module 2 review, notice that this is worth 4 points. Which of the following could not be a probability? Well, we talked about the probability has to be in between 0 and 1. So any number outside of those ranges, answer this problem, right? Because we want to know which values could not be a probability. So if I look at A, 2/3, if I were to decimalize that, that can be a probability. If I were to decimalize the square root of 5, this is 2.3, and this is what? That could not be a probability. So this is one of my answer choices. So I'm not looking for the numbers that can be. We're looking for the numbers that could not be.
Right? So the numbers greater than 1 or less than 0.
That's right. If we look at C, the square root of 1/8, so if I were to decimalize that, I get a number in between 0 and 1, so that's not an answer choice. Negative 3.4, we can't have any probabilities that are negative, so that is the answer choice. And then the last one, 0.7474, that could be a probability, right? So our answer choices are B and D. Okay. We're looking for numbers that are less than 0 or greater than 1. All right, here is number 2. Okay, so remember we talked about the classical definition for probability, which is much like a fraction, the part over the whole. We talked about independent events, dependent events, and their fundamental counting rule. So all of those things come into place here. Well, not all of them, either independent or dependent. So it says if a ball is randomly drawn from a jar that contains 14 red balls, 6 white balls, and 9 yellow balls, find the probability of the following events. So in the jar, we have a total of how many balls? 29, right? So N, which is the total number of balls in this case, is 14 plus 6 plus 9, which is 29. For A, it says a probability that a red ball is drawn. So here we only have one event. So I'm only going to map out one outcome for one event. If we take a look at that classical probability formula, I want to take the total, which is 29, and that goes in the denominator. In the numerator, how many red balls are there to choose from? 14. So the probability is 14 out of 29. Now I'm just going to leave these as fractions just because of the time constraint, but you can always decimalize these if you wanted to. Okay. For B, it says a white ball is drawn. So how many total balls are in the jar? 29. Out of those 29, how many are white? 6. So that's probability, 6 out of 29. For yellow balls, so again, there's a total of 29 balls total. And out of the 29, how many are yellow? 9. A green ball? 0, right? And then for a red or a white ball?
20 over 29.
Right. So we have 29 total. We have 14 red. We have 6 white. So altogether that's 20 over 29. So notice that was that word or. But these events are what? Mutually exclusive, which means they can't happen at the same time. The ball has to either be red or white, We don't have any red, white balls in the jar. All right, so that's mutually exclusive. All right, any questions about 2? All right, number 3. This should look very familiar. Answer the following questions based on the spinner. Each region is equally likely. So there's 12 equally likely regions. So my denominator for this first one, or for all of them really, going to be 12. So A says the probability that the spinner lands on a 9. 1 out of 12. Because there's 12 numbers total. There's only 1 9. So 1 out of 12. B says the spinner lands on a 2 or a 12.
2 out of 12.
Right, 2 out of 12, which reduces to 1 6. The probability of an odd number.
That's 6 out of 12,
Right, 6 out of 12, which is a half. That's supposed to be a 12. The probability that the spinner lands on a multiple of 3.
4 out of 12.
Right, so remember the multiples of 3 are 3 times 1, which is 3. 3 times 2, which is 6, 9, 12, 15. That's going to keep on going. So we have 4, right? So that's 4 out of 12, which is a third. The spinner lands on a number greater than 4. Well, there's 12 numbers to choose from. Out of those 12 numbers, how many are greater than 4? 8, right? Because we can't include 4 because 4 is not greater than 4. It can be greater than or equal to, but since there is no equal to, I cannot use the number 4. So that's going to give us 5 through 12, which is 8, right? So 8 over 12, I can reduce both of those by 4, 2/3, right? And then for F, it says the spinner lands on a number less than or equal to 12.
1.
It should be 1, right? There's 12 numbers to choose from. There are 12 numbers that are less than or equal to 12. So that should be 100% or 1. Any questions about this one? This thing has 12 points. Right, so make sure you understand this one. All right, here is problem number 4. It says a study reports that 64% of all people own dogs. Suppose that 2 people are chosen at random. Are these events independent or dependent? I always kick that with my foot. There's something over here and I just kick it. All right, so let me just start out here. Okay, a study reports that 64% of all people own dogs. Suppose that 2 people are chosen at random. Are the events dependent or independent?
They're independent. It's out of 64.
Well, why would you say dependent?
Depend on them on the dog.
Okay. Well, that can be true. But they're talking about not people owning dogs, but the people themselves. So in that case, it's going to be independent. All right. Because one person, if it comes from a large population, and that is actually the second part of this, the events derive from a large population. So as we kind of talked about, let's say if I sample somebody in Aiken, ask them if they own a dog, and let's say if I go to Charleston somewhere, ask them if they own a dog, they probably not going to know each other. So the relationships on the 2 people chosen, that's the independent concept. And the last one says, what's the probability that both own a dog? Well, how many outcomes? In this one, we're going to have 2 outcomes because we're talking about 2 people owning a dog.
So 6
right? So the probability that the first person owns a dog is 64%. The probability that the second person owns a dog should also be what? 64%. All right, so those are my two events. So I mapped out two outcomes. And 0.64 squared. And there is a key to quickly square something. 0.64 squared is 0.4. It says round to 3 decimal places. So if I look at my third decimal place, I look over to the right. Since this number is 5 or higher, I have to round this 9 up to a what? 1. So that should actually be 0.41 rounded to 3 decimal places. Now, as I alluded to, you can get your calculator to round this stuff. So just to look at that again, if I go into mode, remember there is this little float deal over here. If I want 3 places after the decimal, then I'll go in and recalculate and I get 0.410, okay, which is the same thing as 0.41. If you use this rounding technique with the calculator, make sure to put it back to float. Okay. That way it'll kind of keep all of the decimals after your decimal point. All right, so that is number 4. Problem number 5. Suppose the jar contains 7 red marbles and 17 blue marbles. If you reach in the jar and pull out 2 marbles at a time, at the same time, answer the following questions. Are the events dependent or independent? Well, since you pull 2 out at the same time, the probability of one affects the probability of the other, so those are dependent. The reason why they're dependent is because the marbles are chosen at the same time. C says find the probability that both marbles are red. So we're pulling 2 marbles out of the jar. So we're going to map out 2 outcomes.
So 7 over 24 and 6 over 23.
Right. So the first, well, if I go back, okay, so we have a total of 24 marbles, right? Out of those 24 marbles, how many are red? 7. So we already have 1 red marble out of the jar. So as we're touching the second marble, how many marbles are there to choose from?
6 over 23.
Right, there's 23 total. And since we've taken 1 red marble away, there's only 6 red marbles to choose from. So we're going to multiply the 2 probabilities. So whenever you multiply fractions, multiply the numerators, multiply the denominators. So 7 times 6 is 42. 24 times 23 is 552. 42 divided by 552 is rounded to 3 decimal places, 0.076. Right, rounded to 3 decimal places. Is everybody okay with number 3? I mean number 5, which is worth 3 points. All right, number 6. A dice is rolled twice. So remember, this is just a standard 6-sided die that we're rolling twice. What is the probability of showing a 3 on the first roll and an even number on the second roll? All right, so we're rolling the dice twice. So we're going to map out 2 outcomes for the 2 events. What is the probability of rolling a 3 on the first roll?
1/6.
Right. There's 6 sides on the dice, or 6 numbers on a dice, and there's only 1 3, so that's 1 out of 6. And what's the probability of rolling an even number?
3/6.
3 over 6, right? The even numbers are 2, 4, and 6, which are 3 numbers to choose from out of the 6. So now we can multiply these fractions. So we multiply the numerators. 1 times 3 is 3. 6 times 6 is 36. And if we reduce 3 over 36, we get 1/12. Going down to number 7. It says a quick quiz consists of a multiple choice question with 5 possible answers and a multiple choice question with 4 possible answers. If both questions are answered with a random guess, find the probability that both responses are correct. So now, how many questions on this quiz? There's only 2 questions. So this is just an example of what this looks like. So question 1 has how many answer choices? 5. What color are your eyes? You can have green, blue, orange, purple, red. 1, 2, 3, 4, 5. 5 answer choices. The second question has how many answer choices? 4. So let's say the second question is, what is your favorite dessert? Let's say cake, pie, candy, cookies. That's 4 answer choices, right? So now I'm going to map out 2 outcomes. For this first question, what are your eye colors? How many answer choices? 5. Out of those answer choices, how many are correct? Should be 1. So the probability for getting the first question right on a guess is 1/5. What about the second question? How many answer choices? 4. Out of those answer choices, how many are correct? Should be 1. 1/5 times 1/4, we're going to multiply the numerators. Multiply the denominators, we get 1 over 20. But be careful on this problem because you must answer the question as a percentage. So we have to convert this fraction to a percent. So the first thing we're going to do is convert the fraction to a decimal. Right, so 1 divided by 20 is 0.05. Now we're going to change that decimal to a percent. So we have to move the decimal 2 places to the right and add the percent symbol. So if I move my decimal 2 places to the right, I move it once, twice, it's behind the 5. So the solution here should be 5%. You must answer this one as a percent. Because even though you put 1 over 20 is correct, if you put it in, it's not going to accept it. Okay, and this is worth 2 points. All right, moving along to number 8. It says a study reports that 54% of Americans support increased funding for non-public schools. If 3 Americans are chosen at random, what is the probability that A, all three of them support increased funding? B says none of the three support increased funding. C says at least one of the three support increased funding. So let's look at the first one. All right, so we're surveying three people, so that's three outcomes. What is the probability that the first person supports increased funding? 54%. So I'm going to decimalize that at 0.54. The probability that the second person supports increased funding should also be what? 54. And that should be the same as that third person. So we're going to take 0.54. We're going to raise that to the third power. 0.54. There is like a cube key in here. But you got to like dig through this little math thing, and it's hiding right here. But there's like no fourth or fifth power. So I'm just going to use that little quick cube key, and it's 0. Round to 3 decimal places, 0.157. A 15.7% probability. B says none of the three support increased funding. So again, we're going to map out three outcomes. Now, if there are 100% total Americans in America, if 54 support, how many don't support? I can just subtract, right? 100% minus 54% should give me 46%, right? So the probability that a person does not support increased funding is 0.46. So we simply subtract it from 100%. So 0.46 to the third power is 0.097. Okay, rounded to 3 decimal places. And then C says the probability of at least one. So remember, there was a special definition for that. The probability of at least one, that equals to 1 minus the probability of none. And the probability of none was calculated for part B.
So 0.46. So 1 minus 0.46 is the answer to start with, which is 0.54.
Well, we got to use this value. Oops.
Okay. Oh, okay.
So that's going to be 1 minus 0. Now I want to avoid rounding error. So I'm going to just put in this value. 0.097336. Right, 1 minus 0.097336. 0.903. And let me check that as problem. Yeah, 0.903. So notice for that problem, I did not use that rounded value. All right. You should only round. That's for anything dealing with math. You should only round your final answer. All right, any questions about 8? That's worth 6 points. All right, number 9. Okay. Now on the test, you won't see this little card thing, but you may want to have that handy because you will see a question similar to this. So it says a card is drawn randomly from a deck of ordinary playing cards. What is the probability that the card is an ace or a club?
4 plus 13, but one of the aces is a club.
So remember that addition rule, it was a probability of A or B. That's equal to the probability of A plus the probability of B minus the probability of A and B. You have to take out any overlap. The reason why we didn't use this formula with the previous problem dealing with the pencils is because those were mutually exclusive. The pencils had to either be orange or red. There were like no red, orange pencils. For this problem, it's a little bit different because there's some overlap, and we have to subtract out that overlap. So now if I write this out in words, this is the probability of a club or an ace. I'm just going to sort of put some words to this A and B. So like in this formula, wherever I see an A, I'm going to substitute with club. Wherever I see a B, I'm going to substitute with ace. So this is equal to the probability of a club plus the probability of an ace minus the probability of an ace of club, because we do have some overlap, right? So we're going to see that. So now, what's the probability of finding a club? Right. Well, there's 52 cards total in this standard deck, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There should be 13 clubs to choose from out of that 52. Plus, what's the probability of selecting an ace? Right, there's 52 cards to choose from, and out of those 52 cards, we have 1, 2, 3, 4 aces. So notice there is an overlap. We do have one ace of club, right? So for this last probability, the probability of selecting the ace of club, oops, there are 52 cards to do, 52. There are 52 cards to choose from. And out of those 52 cards, how many are ace of clubs? 1. So I'm just going to put this in the calculator. $13 out of 52 plus, I'm using parentheses for these fractions, 4 divided by 52 minus 1 divided by 52. And we get 0.308. Is everybody okay with number 9? Okay. It's only worth 2 points, but remember there is some overlap. So that's why we use the minus, okay? Now you won't have this this card handout. I guess I can print that out or something if you actually wanted just to have this laid out. Oh, did I? Oh yeah, on that probability thing. Okay. All right, let's look at number 10. This is the contingency table that we talked about last time. So remember with the contingency table, anytime you see the word given, so let me just go through these. So A doesn't contain the word given. It's in E. It is in G. Am I missing something? Okay, well, we'll just see them as we go through. All right. So now if you see the word given, you can't use your row column total. All right. So we're going to see that in a second. So here again, just this contingency table, here's the setup. It's a table of grades, A, B, and C grades. So notice that for our columns, there were a total of 29 A's. There were a total of 18 B's. There were a total of 7 C's. Altogether, there were 54 grades. There were 25 males. There were 29 females. Altogether, there were 54 students, right? And each student got a grade, the two-way table. If you do not see the word given, your denominator should be 54. So let's look at A. It says, find the probability that a student received an A in the class. Since we don't have the word given, we're going to select from all 54 students, right? Out of those 54 students, how many students received an A? So if I look at my total A count, it should be 29. So that probability is 29 out of 54. Now this question carries 14 points, so it's another heavily weighted question. B says find the probability that the student is female. Since I don't see the word given, my denominator is going to be the total, which is 54. Out of those 54 students, how many are female? Well, if I look at my total for females, there are 29 females. All right. So that should be 29 out of 54. Okay. C says find the probability that the student was a male and received an A in the class. I don't see the word given, so we're going to take all students into account. So we have 54 students to choose from. Out of those 54 students, how many were male that received A's? So if I go back up to my male row, notice that there were 19 males that received an A. So my probability is 19 out of 54. All right, if I look at D, D says find the probability that a student received an A in the class given they are female. So what is my denominator here? Well, if I look at my total for females, there were how many females total? 29. And out of those 29 females, how many received an A? 10. Any questions about D? Notice we did not use 54 as a denominator because of the word given. Once we use or restrict our contingency table to only this female row, right? Out of those 29 females, there are only 10 that made A's. Okay. So that's where the 10 comes in. For E, it says find the probability that the student is female given they received an A in the class. So what is the denominator for this one?
29 is the A.
Right. Well, given, you're right. Given they received A's, so the amount of students total that received A's is 29. So that is the denominator. Out of those 29 students, how many were female? 10. So that probability is 10 out of 29. F says find the probability that the student is female and received an A in the class. What's my denominator? Well, I don't have the word given, so my denominator is all of the students. So out of those 54 students, how many were females that received an A? 10. So that probability is 10 over 54. G says find the probability that a student received an A given they are female. So given there are females, there are a total of 29 females to choose from. So that is our denominator. Out of those 29 females, how many made an A? 10. And then H says find the probability that a student received an A and they are female. What is the denominator? 54, because there is not the word given. So out of those 54 students, how many were females that received A's? Should be 10. So that probability is 10 out of 54. And I guess I should reduce that. So if I reduce both of these things by 2, that'll be what? 5 over 27. And I think I'll reduce this one too. All right. Yeah, just make sure you reduce. I may not. Yeah, I reduced everything. All right. Any questions about 10? It's worth 14 points. All right, number 11. It says a state license plate consists of 2 letters followed by 5 digits. How many possible license plates can be issued using this condition? So this is not a probability question. It's like how many possible ways to do something type question. So when you see these questions, you should either think the fundamental counting principle and permutations and combinations. All right. So now this one, we're going to just use that fundamental counting principle. There are 7 outcomes, right? There are 2 letters. That's the first letter. That's the second letter. And then it's followed by 1, 2, 3, 5 numbers. First number, second number, third number, fourth number. All right. All right, so those are the 7 outcomes. For this first character, how many letters are there to choose from? 26 choices. For the second letter, there should be how many choices? 26. What about the numbers? 10, right? If you count on your hands, 0 through 9, all together, that's 10 digits. So there should be 10 choices for all 5 numbers. So now we're going to multiply all this together. So we should have 26 squared times 10 to the 5th power. (26 squared times 10 to the 5th power is, I believe that's 67 million. And let me just write it out first. I'll add the 0. 6, 7, 6, 1, 2, 3, 4, 5. Yeah, 67,600,000 possible license plates. All right, that's number 11. Problem number 12 and problem number 13. Let's look at 12. It says you have 11 volunteers for a play that has 4 characters in it. How many ways can you cast the play? So is this a permutation or a combination?
Combination?
Well, if you're dealing with a play,
Oh, right,
One versus
yeah.
so 11, 10.
so it's going to be 11 permutate 4. And the order would be important. The order would be important because if you're talking about casting a play and runners running in a race for first, second, and third place. The reason why the order would be important in this one is because you want the right person playing like the right role. So if I put this in the calculator, this is 11. And in order to find the permutation function, I'm going to go into math. I'm going to scroll over to PRB, which is probability. I'm going to use that second function. I'm going to put in the number of items we're selecting, which is 4. And we get 7,920. All right. Number 13, it says a basketball team consists of 16 players and 5 people can be on the court at one time, and it doesn't matter which position anyone plays. This is the catch to this problem. So that means that the order doesn't matter. Normally, when you're playing basketball, you want the tallest person to be the center. But in this case, it don't matter. Because it said the order doesn't matter. They just need 5 people to play. This is a combination. Right. So there's 16 players to choose from. So that's our total. And we have 5 people we want to select. So that's 16 combinate 5. So in the calculator, I'm going to put in the total number to choose from. I'm going to go into math. I'm going to find the combination function. I want to put in the number we're going to select, which is 5. And we have 4,368 different ways. All right, any questions about 13? I would hate for you to miss these on the test. Okay, number 14, Jawan owns all 9 books in the Judy Moore series. And how many different orders can we place them on a bookshelf? So he has 9 books. So that's 1, 2, these are supposed to be books. 6, 7, 8, 9. So those are the 9 books we're choosing from, right? And then on the bookshelf, I'm going to map out 9 books. 1, 2, 3, 4, 6, 7, 8, 9. So again, this is not a probability question. It's a how many ways can you order something question. So like we're looking at the bookshelf, and for the first book, how many choices of books do we have to choose from? 9. So let's say I choose that one. Then it's 8, 7, 6, 5, 4, 3, 2, and then 1. This is also known to be a what? A factorial, when you have decreasing integers being multiplied by themselves. So like to find the answer to this, I can multiply 9 times 8 times 7 all the way up to 1. Or I can use that factorial. So I want to put in 9. I want to go back into math. I want to scroll over the probability. And if I scroll down to that fourth function, that is 9 factorial, which is 362,880. Okay. So that'll be the same thing as me like multiplying all of this stuff together. And save a lot of time, especially on the test. All right, so that's 362,880. All right, number 15. I believe this is one of the last problems we answered in the last class. It said 5 different colored 5-sided dice are rolled. We talked about the 5-sided dice. And the numbers showing are recorded. How many different possible outcomes? So since we have 5 dice in our hand, I'm going to map out 5 outcomes for 5 dice. On the first die, how many possible combinations are there? 5, right? In fact, there's going to be 5 for all 5 of those, right? So here we have 5 to the 5th power, which is 3125. So I think the one we had taken a look at that's on the handout was actually dealt with numbers. And then I think they just changed it up and said colors instead of numbers. All right, so that one's worth 3 points. Okay, so we did 16, 17. Okay, I think we didn't do number 19. This is the last one. Okay. It says, suppose that 50% of all students on campus wear glasses. If 2 students are chosen at random, what is the probability that they both wear glasses? Since we have 2 events, I'm going to map out 2 outcomes. The first outcome is the probability that the first person wears glasses. And the second blank is a probability that the second person wears glasses. What is the probability that the first person will wear glasses? 50%, right? Because they gave that to us. What's the probability that the second person will wear glasses? 50%, right? So that's 0.5 squared, which I believe is 0.25. So it's like a 25% chance.